Okay, hi everybody. Welcome to PCB Routing on Saturday. Last week, um, we already started with the board. We got actually relatively far. We're going to start this week with a little bit of a review, look at some of the stuff that we did last week and why we did it, and then we're going to continue on to route more. So this is our board. We have here 8 Ethernet connectors. These are not the normal Ethernet connectors. They're a industrial Ethernet connector. It's called an M12 decoded connector, and it only works up to 100 megabit Ethernet. But on the other hand, it's robust and waterproof, and you screw it in so it can never wiggle out. And yeah, it's dust proof and so on and so forth. So this is what they often use in industrial settings or outside. We have our 8 Ethernet connectors, and then we have one connector, which is our power connector. Since there is no standard pinning for the M12 connectors for power, and the other side is probably going to be wired by people manually in some cases. We're putting the power through 2 rectifiers. Those are these 2. And then right after that, immediately after that, we have our transient voltage suppression diode. This will help any surge or burst or general high voltage events like lightning striking or some other problem on the voltage lines. And we have filters so that we pass EMC so that signals from the outside on the power lines don't come in and screw us up, and so that whatever noise we're creating from inside doesn't get out and cause us to fail. And we have a step-down regulator here, a buck regulator, which steps the voltage down from the 48 volts, or nominally 48 volts. It's usually a bit more than that, especially on the supply side. So we're going to step down here from 48 volts down to 5 for our, the largest consumer of power is probably going to be the Raspberry Pi compute module, because we're not only a network switch, we're at least in one configuration also a, I guess that technically you'd call it an edge device or an edge compute device. Edge being we're the edge of the cloud. Marketing people sadly do dictate what things are called. So yeah, we can configure this such that this connector here is an uplink, and the other connectors are all local area network, so you can connect them to things like sensors and whatnot, and then we can do a bunch of compute on the compute module, and then communicate that upstream via our upstream port. That's what we use this box for commonly. For example, we did one field test where we had a bunch of infrared cameras on here, and I'm not sure how much I can get into details because we did, I think, sign an NDA. So we looked at things with our infrared cameras, and then there were algorithms running on the compute module, which would tell the owner of the giant thing that we looked at with infrared cameras information about it, right? So that would go upstream. Since we were, tied to a pole outside, it's good that it's all waterproof, right? So yeah, with this redesign, we're going to go through all the design considerations. Last week we looked at how to do buck regulators correctly, or at least how to, what to consider when designing a buck regulator. And I actually forgot this track last week because if we disconnect this, ground is already connected, so the layout is not going to tell us that there's a problem here because these vias go to the ground layer and these vias go to the ground layer, right? But the problem is we want a very low resistance, but especially low inductive resistance, right? And so there's different kinds of resistance, if you will, right? There's the DC resistance, which you have through a resistor, right? But if you're switching on quickly, then the initial resistance in the first nanoseconds or picoseconds or whatever is going to be mostly the inductive resistance of having to build up the magnetic field around the wire, right? So the more wire you have and the more bend around in a circle it is, the more inductive resistance you're going to have, right? And since this regulator is going to be switching on and off relatively quickly, there are some that switch in the tens of megahertz. This is only so high kilohertz, I think. So it's definitely less of a problem here. I mean, this would probably work and would probably still pass EMC since they're very close to each other and everything else is done right. And we have the big filter upstream, but we definitely don't want to gratuitously cause any noise that we could otherwise avoid, right? So we definitely want to connect this like this, right? So let me switch you guys back to the schematic. This is actually the connection between here the chip and here the inductor, right? So this is pin 1 is going to be switching on and off and on and off the whole time. What switches on, then we get a current flowing from the 48 volts into the inductor, and changing high voltage drop into magnetic momentum, right? And we switch it off, then we're going to use that magnetic momentum that we built up to pull essentially charge from ground up through the inductor, and that's how buck regulators work, right? So that's going to be going on and off and on and off and on and off. So if we add resistance by not having this connection, by making it go through the board, down to the ground plane, and then back up, right, then we're increasing the inductive resistance, which is going to make our buck regulator less efficient and a lot more noisy, right? So I forgot that last time, and good thing I caught that. One more tip, which might have saved us here, is the way one lays out the stack up, right? So I have a fill here, which is going to fill all the, it's going to fill the top layer and the top inner layer and the bottom layer all with ground. So they're going to be filled with copper connected to ground, right? Any extra space. And so that would have been a very, low ohmage connection between these vias here and these vias here. But one thing that you should take notice of is if it's going all the way down through the entire board. Let's get some measurement here, because the entire board length is something like 1 point. Oops, it doesn't let me slide the window out of the way. Okay, let's do measurement here. I usually just hit the button, but it's off screen because I had to make the screen smaller so that it would work on the stream. But I think it's here somewhere. Tools. Am I blind? No, I'm not seeing the measurement tool. And I can't really get to it here. Oh well. So the distance here is going to be, we can see down at the bottom, here we're at coordinate 81 and here we're at 79. So it's a couple of millimeters, right? Sorry, the good visual aid is the track is 1 millimeter wide, right? So we're, maybe 3 or 4 millimeters long between the chip and the diode. So pin 2 of the chip and pin 2 of the diode. So if we're actually going through the whole board all the way down to the bottom and then back up through the whole board all the way to the top, and the board's 1.6 millimeters, right? That's already over 3.2 millimeters of distance just to get down to the bottom and then back up to the top, right? And so if we look at the flood that I filled that I did, the ground planes, then I didn't pick N2 to be the ground layer. I picked N1 to be the ground layer because the chips are all at the top, the red layer, right? And so if I use the next layer down as ground layer, the way the board stack up works, well, this is going to be different for different PCB manufacturers, but most PCB manufacturers are going to have a board stack up of top layer, very thin space between them, first inner layer, and then a large space, and then the second inner layer, and then a small space, and then the bottom layer, right? So the distance between the top layer, the red and the green here, right? So the top layer and the first inner layer is going to be, very, very short, right? So, it's always good to put ground like immediately under the chips. I mean, okay, some boards you do both sides, but that's actually a lot more expensive if you're for the pick and place machine, right? Because they have to worry about putting all the chips on one side and then they have to turn it over and then they have to put all the chips on the other side. And it can't just go through the machine just in one go. And then you have to worry about the heavy chips falling off the bottom because they're just stuck on with solder paste before they go through the oven. And then, yeah, it's back in the beginning of my career, I always did like 2-layer boards and try to make them really small because I thought, oh, well, board space is the expensive thing. No, board space is not an expensive thing. Like, a square decimeter of board, 10 centimeters by 10 centimeters is only about, I don't know, $1 or something. Boards don't cost all that much. It's the machine time for the pick and place machine is what you're paying. And so if you can put everything on one side, then it's a lot cheaper, right? And so if you have a board where all the chips are on one side, then put the ground layer like immediately under the chips, because then you have a considerably shorter path through the board to the ground layer. Okay, so that was my screw up from last week, and we fixed it, so we're all good. This week, I think we're going to look at both the switch chip up here, and we're going to look at the power over Ethernet chips. Here's one, and I think down here is the other one. Yeah, power over Ethernet controller. Because we're not only an 8-port switch, we're also providing power via the power over Ethernet standard to the other devices, right? And this is important because people don't like installing wire. If you have a power over Ethernet device, then there's just one wire, and probably more importantly, everyone's allowed to connect it, right? As soon as you have like power lines that are not in an Ethernet cable, then you sometimes have like a subset of people that are allowed to connect it, depending on your country's laws or your plant specifications and whatnot, right? Because there's nothing you can really do wrong with power over Ethernet, but if you have, power wires going places, then you can definitely do stuff wrong, right? So, yeah, the fact that just anybody can, is allowed to, can save you somebody having to drive there just to turn a screw, put a wire in, and turn the screw again, right? That's kind of a waste. So, yeah, we're gonna have, there's probably going to be different sensors or potentially actors, but we mostly do sensor stuff so far. Actors are hard real-time dependent, and that doesn't work so well over Ethernet, although in some cases it can. Yeah, most of what we do is monitoring systems. So if you're monitoring stuff, well, you're basically just reading, right? So yeah, so there's going to be sensors on there, and we need to power them, and so we're going to use the power over Ethernet standard to power them, and that's what these controllers are for. And I guess if we want to get into that a little more, if people want to learn more about power over Ethernet, then just put it in the chat. I did a poll last week, and it seems like people wanted to learn a bit more about the EMC testing side of stuff. But as far as Ethernet goes, that's actually relatively simple because the magnetics actually save you, right? We talked last week about how the magnetics work with Ethernet, and yeah, that it's hard to fry a wire with electrostatic discharge or something, and you're not going to get any DC current passing through the magnetics, which is why Ethernet works well in large offices or whatever. You can connect things to other rooms, right? Because there's actually no DC electrical connection. It's just you're basically just moving electrons around in a circle with magnets, send data, right? So I think what we're going to start with is probably the switch chip itself. Now, it has a bunch of periphery, so it's going to need things like decoupling capacitors and a crystal and whatnot. Why don't we start with the crystal, because that's kind of easy. So here's the crystal, and one thing that you have to worry about with crystals is they have to fit with the chip. So like network chip in the data sheet is going to have a specification of which crystals will work with it. And usually, most chips work with most crystals. The problem is if they don't work, then it's not that they won't work at all. It's just they won't work at some temperatures. They won't work after a certain amount of life or whatever. So, I mean, the worst thing that can happen to you is that something works in the prototype and then dies in the field, right? And so, you definitely want to make sure that the type of crystal that you're using as a timing for whatever chip you're using, that actually works with the chip. Different crystals have things like startup energy, like how much energy you need to get it swinging, and how much energy you need to keep it swinging, and how noise immune it is. And they also have like a characteristic, what size of capacitor they need to dampen them, right? And so depending on the crystal, you might have 12 picofarads, you might have 22, you might have, I mean, some of them even start at like 5, and go up even higher than 22. But I actually just used the same crystal out of the demo design from the manufacturer. I mean, that's the lazy way to do it. If you can actually buy the crystal and it's cheap, right? But in this case, it's a widely available crystal that they're using in the demo thing, and yeah, so I just on the safe side, right? So one thing to think about when testing your design with crystals, if you think something's going wrong, the tips of oscilloscope probes are also have a characteristic capacitance, right? Like I think they're usually 12 picofarads, and then you're going to have some inductance through the cable, and you're going to have I think nominally a mega ohm of DC resistance, but you're going to have more than that DC resistance because you're going to have the wave resistance part because you're going on and off and on and off, right? So you're going to have capacitance of the probe is going to also dampen the signal, and so when you're measuring signals coming out of crystals or going into crystals, the oscilloscope is probably going to be enough of an extra load that the crystal has to bear that you're probably going to screw it up just by measuring it, right? And so, yeah, it's actually kind of hard to measure crystals, right? You need like an active probe or something like that. So yeah, so another reason why we definitely don't want to get this wrong is if we get it wrong, then it's hard to debug. Yeah, the measurement is going to be intrusive enough that we're going to change it because I mean, for maybe your gut feeling, like there actually is a tiny piece of crystal in the form of like a tuning fork that's actually moving inside there, and that movement of that really really tiny piece of crystal is the energy that is coming out of there, right? It's actually bending, and because it's a quartz resonator crystal, it bending is creating electrical voltage, right? And so, yeah, I mean, it's kind of intuitive that measuring something that small and finite amount of energy, if that has to move the whole wire inside the oscilloscope cable up and down, then yeah, I mean, to me at least, that's intuitive that's too much energy taken away for it to continue working, right? But also to that same point, we don't want to make the wires to the chip go all over the place, right? We also don't want the wires going to the chip going close to other things that might influence them, especially if we're relatively close to the 25 megahertz of the crystal, right? If we're close to the crystal frequency, but just a little bit above or below, we can actually make the crystal, influence the crystal frequency such that it's wrong. If there's well, it's called crosstalk, right? If you have two lines next to each other and one's influencing the other. Um, Way back in the day, I was almost 20, I know it is 25 years ago now. Damn, I'm old. Uh, um, the first design I really, the first at least big design I ever made, I had a switching regulator pretty close to the crystal, and the crystal was like nominally, I think, 1 megahertz, and switching regulator was 400 kilohertz. And I also did it wrong, and so it was very noisy. And it turns out the 400 kilohertz was enough to make the crystal run at 400 kilohertz. And yeah, I mean, that design was an MP3 player, and the crystal was for the digital analog converter. And so the symptom was that the music came out really slow, like less than half the speed, because it was nominally running at 1 megahertz, but it was actually running at 400 kilohertz because there was crosstalk between the DC-DC regulator and the crystal. Yeah, I think the first song that came out of that was Britney Spears, but she had a really low voice. Uh, yeah, stories of lore of a long time ago. Um, so in our case, we want to put this, very close to the chip. Um, so the question is if there's anything that has more priority than, to be close, than the crystal has priority to be close, right? So if we're looking at these pins, I guess you can kind of see it in KiCad. This is another reason why you should name your nets. I think I may have actually broken that rule here with pin 52 and 51. Um, let's switch here. Yeah. Okay. So I didn't actually name these nets, which you can see there's an old design. This goes against our current design guidelines. So let's name this just XO. I don't have another crystal in the sheet, do I? No. Okay. I guess the labels are go across sheets. Oh, no. The cross sheet panes go across sheets. So this one's, oh, and this is snapping to the wrong grid. Oh, I hate it when the grid gets messed up. And I hate having to like make the grid small. Oh my God, what's wrong with this grid here? You can tell this is a, what? Old design. Okay, am I gonna like have to, okay, let's see if that's, for maybe some context of what's going on here. KiCad has some problems with like maintaining grid if you upgrade it from like if you made the design in an older version of KiCad and then upgrade to the new version and then save it. Also, when you drag things around, sometimes if you like it will snap to like the center, but if the center is not like, if the center is like half a grid or something, then it'll align to that. And so you can get these alignment problems. Okay, let's go back to a more sane grid. And yeah, okay, that seemed to have helped. So let's label these XO and XI. X is crystal, right? So that's out and in. I got them right way around, yes. Okay, so now if we switch back to the schematic and update it, then we actually have these pins will be named correctly. So that definitely helps if you're looking at what things are, right? So Yeah, generally I'd suggest name all your nets that aren't just obvious, right? Like if you have, you know, resistor and then a capacitor, then the connection between the two, okay, maybe you don't need to name that one, right? But anything coming off the chip, then give it a name, and that'll help you when laying out. Okay, end of tangent. um, so we have pins 49 and 50 are voltage, right? And um, you know, one's analog and one's digital. I'm not actually sure what analog means in this case. I guess it, you know, the crystal's technically being driven by an analog circuit. We don't really have analog here. I'm guessing that the, you know, non-VA version, like the pin 49 version, is actually driving the external pins, and the other one is driving the internals of the chip. And the reason why they're separating them is they don't want. I mean, the one driving the pins, well, that's actually driving a potentially a pretty big load, right? Especially when they first switch it on, you're driving against the whole capacitance of that diff pair, right? Um, you know, the tracks have a capacitance to ground, they have capacitance to each other, and all that. And so when you're switching on, I mean, this chip is dead, you know, going to have to switch at relatively high frequencies. You know, 100 mbit Ethernet is going to be 125 megahertz. I think because they don't count some of the bookkeeping bits in the uh, nominal 100 megabit thing. That's why it's, you know, not 100 megahertz. It's 125. But anyway, so when they're switching 125 megahertz, that means uh, transistors that are switching it on and off are going to have to switch quite quickly, and that means that they need the power quite quickly to be able to put it into the line, right? Otherwise, the voltage drops, right? So if you're switching a load up, then you need somewhere to draw from, or if you're switching a load down, you need somewhere to draw from, or else your negative rail is going to go up and your positive rail is going to go down, right? If you don't have something to draw from. If you're drawing all the way from the power supply, well, that's a lot of parasitic inductance. I mean, every wire is also an inductor, right? You know, they're usually very small inductors, but if you're switching big loads at high frequencies, then that's enough, right? So that's where this topic of power integrity comes in, right? Power integrity is basically the discipline of maintaining, you know, somewhat nominal voltage on pins, even with changing power needs, right? So when the chip switches, it's going to need a lot of power for a very short period of time, and then less again, right? And you know, if it has to draw that power from way far away, then the inductive load and you know, the nominal resistance of the tracks as well, but it's mostly inductive resistance, is going to kill you, right? So you're going to have local power drops, and so that's probably why I you know, isolated the actual driver pins from the outside from the core of the chip, because in the core of the chip, if the voltage drops there, you might, you know, flip some bits, corrupt your data, crash, whatever. Right? So uh, if we want to be good power integrity stewards of our chip, then we definitely want the coupling capacitors to be very close to the chip, right? So that's why there are so many little capacitors on newer boards, because of power integrity, because we want okay, so that's connected to there. That's some other thing. Oh, I got the grid. I got the grid here very coarse. Let's make a finer grid so the chips land a little more. Okay, so I'm not quite sure. Yeah, okay, so that's probably the right one for that. So we want to put these relatively close, or yeah, I mean, basically as close as we can to the chip. I mean, if you look at a lot of modern boards, like if you look at the um, self-driving computer board from Tesla, then it's on one side, it's all just capacitors, right? Like the entire board is just capacitors. So where do we have the normal 3.3 volt capacitors? Where are those guys? oops. So that's the problem. I have a big net. So if you start routing, then it'll highlight all of the capacitors around that are on that net. Okay, so we got one here, one here, one here. So that's what, 1, 2, 3, 4, 5, 6. And we have one capacitor, two capacitor, three capacitor, four capacitor, five capacitor, six capacitors. Okay, so it does work out. I'm not quite sure why they landed the way they landed. But regardless, let's just take this one and put that one right next to this one. I like putting things in rows. Maybe it's just my OCD, but it usually looks better that way. And it's easier to find space for the silkscreen designators for the parts. Okay, so if we're this close here, then that's going to be definitely close enough. But it's actually a loop, right? If we're drawing current here, well, we're also drawing current from ground, right? Because we're drawing current in relation to ground. So if we think about drawing energy from this capacitor, well, the distance traveled, if you will, is going to be from the whole loop of how ground connects into the chip and how the power connects into the chip, right? So we want to make sure that we're going to the ground plane immediately. That we had, I talked earlier about how the ground plane should be close to the layer with the chips on it, right? So we don't have to go through the whole board. Because again, this track is 0.2 millimeters wide. So we look at this, we're maybe a little more than a millimeter away from, between these two pins. The board's 1.6 millimeters thick. Well, that's a pretty big distance to travel in relation, right? So we're going to this ground pad. And so here you can also kind of see, just as a gut feeling of how close you need to be to the chip, right? They have one big ground pad in the middle, and that's like 6, 7 millimeters away from the edge, if you will, right? And so, yeah, we don't really have to worry so much on this. You can also calculate, what 125 megahertz speed of light, and then divide it by 3-ish, because electricity through boards with capacitance and inductance of the wires and whatnot, slowing it down, is not going to go at the speed of light in a vacuum, right? And so, yeah, that's kind of the wavelengths that you're going to be dealing with, and you want to be considerably smaller than that, right? Yeah, if you calculate that out, then it's multiple centimeters still. Yeah, it is something to be very careful with, but it's we're pretty fine here. But that does take, being close in that respect does take precedence over being close with the crystal. So we're going to get the power integrity part here going well. Now let's, why is my monitor getting darker here? Maybe because I'm sitting in the office in the middle of the night. That's not quite night yet, but yeah, local time is 9:30, so it's the only time a father of young children can, yeah. Let's see, make this brighter. Okay, sorry about that. Now I can see again. So yeah, okay, so the next lines are there, and then here, this will probably be some power integrity thing as well, because if it's 1 volt, then that's probably the core. So you want to make sure that that's short. And it's not actually a problem with the clock lines being close to these, because the power lines are at least nominally not changing voltage much, right? And so you're not going to have a lot of crosstalk here. So if we route these out like this, then we got plenty of room for this next guy to be close to his pin. There we go. And let's put the crystal like about here-ish. I guess we could maybe go more like that. That should, oh, that's not fitting between there. As I said last time, 0.2 millimeters is a good kind of standard if you don't have any other any reason to do it differently. But most PCB manufacturers will also be able to do 1.5 millimeters, let's say, and that should be able to get us through there. Oh, no, not 1.5, 0.15. 1.5 millimeters is huge. Ha ha ha. Okay, 0.15. Yeah, okay, like the cheaper boards are 6 mils. We're at 5.91. That's 6-ish in non. Oh no, so we're even still not going to be able to get through there. So I guess we'll go around. Is that going to change where I want to put it? Yeah, a little bit. Let's put it like there. Oh, it's because it's the small crystal. Yeah, there's two sizes of these SMD crystals, and this is apparently the small one. So let's go like up there, like that. This is actually just looks kind of crappy, so why don't we make that a little more beautiful? KiCad doing weird stuff. There we go. Oh, you're still doing weird stuff. Well, I'm just gonna do that. Make it pretty here. Okay. Why is KiCad doing weird stuff there? There we go. There's like urban legends of 90-degree corners being a problem because acid could get trapped like in that corner. And that's maybe used to be true when back in the day when people hand etched their boards and kind of tipped the acid out and whatever. That's not true anymore with modern PCB manufacturing. Like you can do 90-degree corners, it's fine. And also, 90-degree corners as far as wave reflections or whatever. That's only true if your lines are, somewhere close to the frequency, right? Like, lower frequencies can go around, lower frequencies compared to like the width of the track and the length of the track and whatnot, which, here we're, 25 megahertz and the, track length is tiny. It's not going to be a problem. Yeah, there are plenty of RF nerds on YouTube that'll give you a better explanation on that than I can. But I'm here to calibrate your gut feeling. Yeah, and gut feeling is it's fine. Like being short, short tracks is a godsend, right? That heals a lot of evils. Why can't I? Yeah, there we go. Well, I guess yeah, maybe this is a good also thing to talk about. So if I put a via here, right, in the pad, right, the via has, at least in the the cheapest vias are they drill a hole in the PCB and then they coat it with copper, right? There are different ways to do that, but yeah, but there's still a hole in the middle of the via that goes through the board, right? And if we're putting solder paste here on pin 2, and then there's a hole that it could theoretically drain down when it gets when it melts, right? When it gets hot, then you could potentially drain all your solder paste away down into the via rather than it actually working with the crystal. And it's another one of those problems where it'll probably work on your prototype. Like the chip is probably touching the metal well enough that when the solder melts, that it'll stick to the chip first, and then the surface tension will keep it all up top where it needs to be rather than it going down through the via. But, maybe there'll be, one batch sometime in the future, after the engineer that designed the board has left the company and all that kind of stuff, um, where it doesn't work that way and you're going to get defects. And so, if you do want via and pad, it can be very handy being able to put vias and pads. Then you definitely want to go with plugged tented vias, right? Which basically means they put something in the hole so that the solder can't go through it, right? And that's more expensive. It's not that much more expensive anymore, but it used to be way more expensive. Okay, old guys telling of the days of yore. Anyway, um, so if we want to have a cheat board, right, then we probably don't want to put this in the pad, right? So if I select it and hit G, then it will let me drag it around and show me what it's having problems with. I guess when I made the grid smaller, maybe I could get it in between those to the point where it's not too close to the pad. No, it's still snapping. Why is it snapping that much? Okay, there we go. So that should be okay because actually this white part here, this is where the via has copper showing, right? This red part is where it actually, it has copper, which is covered in the insulation, what's it called? Usually I have everything in English in my mind. Stopplack in German. Uh, the covered by that green insulation layer, right? So, uh, yeah, this should be fine, right? We're not going to be bleeding solder that far away and then down into the via. Um, that's actually a common mistake that I've also made. All of my sins come out in the stream. Okay, and we definitely want to put these stabilizing capacitors of the crystal pretty darn close. First of all, because we also want to keep the tracks to the crystal short, right? So they don't catch a bunch of crosstalk. But also because we want if we have long lines going to these capacitors, then again, at this frequency we're going to have some wave resistance. Wave resistance basically just means that the lines have capacitance and inductance, right? And so the inductive resistance the wave has to overcome while traveling through the wire and filling up all of the capacitance on the way. That that yeah, when you're switching, that also is a resistance, right? And yeah, I think the wave resistance is like characterized by the ohmage of a terminating resistor with which you don't get reflections or something like that. But again, there are people that have way better explanations for that kind of thing on YouTube already. I'm just here to calibrate your gut feeling. Ha, ha, ha. Anyway, so gut feeling says short is good, and that's definitely short enough. We'd be okay if it was another half a centimeter further away or whatever if we had other reasons. But yeah, generally we'll just want to do best we can. Okay, here we definitely want to be relatively close again with our via because we're in a power integrity context, right? We want to maintain the power integrity of this 1 volt, which is probably the core voltage. Let's see what this is. Oops. I guess I have to actually select the chip that it's connected to. Although I can already see, since this is a resistor, it already has resistance. It already has a bunch of parasitic inductance and whatnot, right? So there's not going to be large amounts of power flowing through a 2.49 kilo ohm resistor, right? So generally, this probably doesn't need to be super close to the chip. If there's no other reason, then we can put it close anyway because we because it's, aesthetically pleasing and it'll give us more room to route other stuff. But yeah, I mean, if this was like, I don't know, a mega ohm, then again, I'd be back to worrying about crosstalk on the line because, if it's uh, mega ohm, then there's going to be very little current flowing, and so if we have a wire next to it that's noisy, then we're going to be messing with it. But 2.49K is something like single or double digit kilo ohms is kind of the sweet spot where there's not going to be a lot of power flowing on the one hand, but also on the other hand, there's enough potentially flowing that you don't have to worry about crosstalk as much. And so, just by that, kind of explaining my gut feeling here, even though I don't know what this does, I know that it's not going to need to be really close to the chip. And now let's go look at what it does. IB riff. Oh, this is like a strapping resistor that decides like how I think uh, how strong the transistor switch. So I guess this is maybe tuning it to the magnetics that we're using. I just use the normal one out of the data sheet because at this point, like, I mean, this is a pretty old switch chip, which also means that it's cheap. I think it's like $1 or something for an 8-port switch chip, which is just insane. I mean, remembering spending $100 on a switch back, 100 megabit switch way back in the day, right? Now it's $1. But yeah, so way back when, then, there were a bunch of different manufacturers of magnetics and whatever, and so you had to tune it. But here in this case, yeah, I mean, the 2.49K is just coming out of the data sheet as the standard thing for normal magnetics. Okay, here, though, the next pin is going to be power integrity relevant again, right? And so that's going to take precedence over this resistor being close to the chip, right? So this guy, I think, is the chosen one. So let's make it the same place, and then we'll sneak this wire out between them and then put that one further away. So this, let's see, we can put this via somewhere else. Now that could potentially bleed, but we actually do have the space to move these down, so we can just put that via there. That's going to be enough-ish. And then we're going to take this one and sneak it out. And it can actually just stay right where it is, actually, because we're going to need a little space to put the text labels. I mean, this size. PCB manufacturers are going to, tell you how big the smallest letters are that they can draw, but at this point, they're usually smaller than is, visible for someone who, needs glasses or whatever. You probably want to stay within that range of, normal people can see it. Where's this guy's? Okay, C39. Let's see. So let's switch to the, yeah, okay. So if we do that like this, and that's all kind of right. I guess if we have a chip here, then we can put it here, and then it's still clear who's who. Yeah. Okay, so next pin. Okay, now we're getting into the pins for the actual magnetic chips, right? So why don't I just kind of demonstratively route these out to make sure they all fit. Okay, then we have another potential power integrity thing here, right? I mean, the reason why we have these all spread out around the chip is because the drive transistors are spread out around the chip, right? Like here we're driving these two diff pairs, or probably just one of them because the other ones, receive. But yeah, here we're driving them, and so each diff pair or pair of diff pairs, I guess we have some more up here, is going to have its own decoupling capacitor. Okay, so just grab one at random. Oh, they seem to all be 1 microfarad, so I don't really have to worry about some needing bigger ones, and there's a right number of them. Okay, so let's just put this here. We're probably over optimizing. I mean, if we put, what centimeter of track first, and like this big chip is, I think, 2 centimeters wide, so just to give you a feeling of how much a centimeter is. Then no, it's not even 2 centimeters wide. Yeah, anyway, if we put it a centimeter away, it'd probably still work because 125 megahertz is actually still not super high frequency. I mean, if you're routing FPGA stuff or whatever, then you can certainly get into the gigahertz, or your PCI Express bus or whatever. I mean, there you really have to worry about it because, yeah, I mean, it all comes back to the switching frequency. I mean, if we want to be pedantic, it comes to the frequency that the transistors switch at, right? So the time it takes for them to turn on and off is the actual thing, but that's going to correlate strongly with the speed of the bus, right? Like nobody's going to invest money into making, using transistors that could switch at 5 megahertz if they only have to switch at 5 gigahertz if they only have to switch at 125 megahertz, right? Okay, so this via really doesn't matter because it's resistor, right? This via again will matter, but we can just put it right here. Again, as close as we can without bleeding solder into it. Let's connect that. And I mean, another thing that we probably have to think about eventually is this, this line, for example, is going to be connected to a bunch of other stuff. Oh, apparently not a whole lot of other stuff. But yeah, it is going to be connected to some other stuff at least. And so we're going to have to put a via here somewhere. If we put the via like here, then we're going to be, if this pin is noisy, we're going to be sending that noise through the line to somewhere else, right? But if we put it here, then that noise is going to be dampened by the capacitor, which is right next to it, right? Like there's going to be voltage drop across this line when we have quick changes in current flowing, right? Because the DC resistance, the normal resistance, is minimal, like, I don't know, like single-digit milliohms, if that, right? It's a tiny short track. But the inductive resistance could be higher than that, right, if we're switching fast. And so if we put it like over here, then we're going to have, over here, then we're going to have like some voltage drop across the line, and I mean, it's kind of the same thing that we were talking about yesterday, or not yesterday, last week with the transient voltage suppression diodes, right? If you have voltage drop across the line and you put the via at the other end of the line, then it's going to see the voltage drop, whereas if you put it right next to the capacitor, then it's not going to see the voltage drop. Okay, let's keep going around. So yeah, so we're probably going to put like a via here later to connect to the rest of the 3.3 volt. I sometimes like to just put down vias so that I know where they are, and I'm going to eventually connect them later once I see this whole geometry of the power and whatnot. Okay, let's route these out because this is another Ethernet connection here. Now there is going to be a spacing between the wires and width of track and whatnot, which is going to give us the right wave resistance for these differential pairs, right? I mean, the reason why differential pairs are used so commonly in higher frequency stuff, and the reason why we couldn't do higher frequency stuff years ago, right? Why it used to be hard is if you have a single line that you're driving up and down, well, you have to drive the capacitance of that wire to the whole world, basically, uh, um, you know, uh, the uh, falls off at R over three, at least between R to the third, right? If it's point to point capacitive thing. So the world is generally far away. So it's mostly just close stuff, right? Okay, it's R over two for a line, and it's oh, sorry, no, it's R over two for a point to point. It's R over one for a line, and it's just R for if you had an infinite plate, but you don't actually have an infinite plate. But yeah, anyway, so with my somewhat coherent ramblings, what I actually mean is if you have a line you're driving up and down, there's going to be a capacitance between that line and stuff around it, right? But if you have two lines and you're driving one up and one down, the sum of the two is going to be zero, at least if you're far away. I mean, they're not zero super locally because they're not in the same place, right? But as soon as you get a couple of uh, um, track widths away, then they cancel each other out, right? So you're driving a lot less capacitance, and the magnetic fields that you're building up, well, they're going one direction with the one line and the other direction with the other line is where power is flowing, right? So that again is going to cancel each other out from a magnetic field perspective, and so the parasitic inductance and capacitance are both lower with a diff pair, right? And so that's why we can go at much higher frequencies without causing as much noise and also without having to put as much power into it with diff pairs, right? And so by I guess it's like the same way as you have with light if you're a physicist, or waves on water if you're kind of a normal person that actually wants to see things. If you're at the beach and you watch waves and there's like a sandbar where the depth of the water is different, you're going to see that uh, uh, changing the way the waves act, right? Like it'll slow waves down if there's a sandbar, so they're going to no longer be these straight waves coming into the beach. They're going to kind of curve around that, and then depending on how wide the sandbar is and how what the depth difference is between it and other things around, you're going to maybe get some reflections of waves going back out into the ocean, right? They come up to it and they go back, right? And you have the same effect with wave resistance going through lines, right? It's also kind of the same effect with light propagating through material. So you have different light speeds and different materials because the propagation it actually has to physically get through, right? And that's if you get into the physics of light propagation, that's why things reflect off of surfaces, and that's why it's also why signals reflect off of things in copper tracks, right? So if you have two sections with different wave resistances, right, then at the point where you're going from one to the next, then you're going to potentially have reflections and generally screw up your signal at that point, right? So again, gut feeling, how important is that, right? Yeah, I think the Ethernet tracks are something like 50 ohm is your goal. But if your track is considerably shorter than the wavelength of the wave, you're usually still actually good. Like if you were picturing your sandbar in the ocean and it was just tiny, like it was just, I don't know, one not actually a sandbar, just one metal post sticking up halfway through, then that's just so much smaller compared to the size, to the wave, that you're not actually going to change much, right? So if we look at these pins, for example, right, of the connectors, um, they're a ways apart, right? They're big and thick. I mean, that's definitely not going to be 50 ohm wave resistance going through there. And then the cable is probably going to be, at least if it's a somewhat uh, quality cable, then that's probably going to be the nominal wave resistance, right? Uh, they'll use the right insulation thickness around the wires and the right insulation dielectric. The capacitance is not just the distance; it's also like how many electric dipoles are there, that you can physically spin around in between there, right? So give you the capacitance of whatever the insulating material is of the wire, right? So that's going to be the right wavelength resistance, but the connector isn't, right? Because they're using the same, 4-pin connector that I think there was originally just industrial sensors used this connector, and then they made a different coating. The coating on these M12 connectors basically just means the way the notches are cut into them, right? So that they don't all fit in the other ones, right? But the pin size and the distance between the pins, that was not uh, devised with Ethernet in mind, right? So that's definitely not going to be 50 ohm wave resistance, but it still works because the connector is relatively short compared to the wavelength of the Ethernet, right? And so yeah, I mean that again, sort of just to give yourself a gut feeling of like how bad is it if I use the wrong wave resistance, right? The other thing is the uh, reflections are have two potential downsides. One of them is that with enough reflections you're not going to see your signal. The noise will be louder than the signal, and you're going to start dropping packets, right? But the other problem would be that you start emitting stuff on other frequencies, or uh, because the signal with reflections is a different frequency, then you have different skew problems and whatnot. And basically, you don't pass potentially don't pass compliance with the electromagnetic interference transmission side of things. Now, I actually almost there. The one EMC test that I almost failed. I did this completely wrong. I was early in my career and I didn't even know how to calculate wave resistance, and so yeah, I mean rather than using the right size tracks, I had something like this as the connection, right? So, not even a diff pair, not close to each other, whatever. What saved me was that the tracks were short. They were about this length, right? So, centimeter-ish. And so I still passed EMC, even though just by a little, even though I used, the wrong track width and routed them weird and blah, 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 right? So, yeah, you should do your best, right? But 125 megahertz is still not high, right? Like once you get above a gigahertz, then you really, really have to be careful. But yeah, I mean, imagine 10 times less track that you could screw up, right? As far as the distance, that would be quite critical here, right? We're getting into the limits of the geometry of common chip forms, which is why a lot of chips that work in that frequency are ball grid arrays rather than the quad flat packages. I mean, the geometry of the signal frequency, the signal frequency dictates the geometry of the chip, right? So kind of went off a tangent there. Basically, what I'm trying to say is the fan out right next to the chip, don't really worry about the wave resistance there too much. I mean, you definitely want to keep them close to each other, and you definitely want to keep them somewhat the same length. That's pretty important, because if they're not the same length, then you're going to get skew, right? You're going to get the signal arriving on one line earlier than the other one, and then the trick with them canceling each other out doesn't work anymore, right? Because at the leading edge of the wave traveling through the lines, they're not going to be canceling each other out because one will be further along than the other, right? So yeah, you want to keep them relatively the same length, in some relation to the total wavelength distance, which is many centimeters at 125 megahertz, uh, and keep them close together. Like, don't do what I did early in my career with the not putting them next to each other. Uh, yeah. Other than that, like, just the power integrity side is probably more important than getting that perfect from the first centimeter, right? Uh, okay, so we got those kind of rooted out just to show us where this space is. So with this one, I think I'm just going to put that one still in our row here on the side, even though it's actually technically over there, just because we have room, and it's kind of the same length anyway. Okay, I guess I had them a little further away from the chip. Like I said, pick and place machines have gotten really good at getting really close, like they don't actually grab the chip and they suction it on with a tiny vacuum suction cup from the top, right? And those have gotten really fine pitch. So yeah, you don't really have to worry so much about putting chips really close to each other anymore. But yeah, I still, just because maybe I'm gonna have to hand solder that off, and over here this chip is a bit taller than the resistor is going to be. So I'm gonna have to be able to theoretically get a soldering tip in between there, uh, if the prototype doesn't work or something. So yeah, I mean that's the only reason I'm not putting them right next to each other. Okay, here again we have normal fan out of the Ethernet. So we're gonna do something like this, so we know you can get them out of there, because eventually, yeah, there we go. There's the other capacitor. So let's just take one from up here and put it, yeah, again, that distance. I mean, I'm not going to have to take the capacitor off, but just for my OCD, make them all about the same distance. Okay, and then we have fan out here. Hope I'm not going to have to switch around like where the Ethernet things are, because theoretically it doesn't really matter which port is what, right? And so if it's hard to route them on the board, then I'm going to have to switch them around in schematic. Okay, so here we have another power integrity relevant. I wonder why we have two. I guess it doesn't really matter. Definitely does give us some space here. So let's put this one here, and then we've got another fan out. Oh, we got plenty of room here though. I'm just putting these tracks here as kind of a placeholder. I might make them short and go directly to VOs immediately or something on some of them, but just to make sure that if we need this space, that we have the space. Put this up here because we got room there. Okay, so that, and then what's this? Okay, that's fan out again of the Ethernet lines. This is kind of boring watching me do fan out a bunch of times. There's not much to talk about. Now let's scooch them all the way over so that we have room for capacitor there. So we got another 1-volt one. That's probably core. Also, leaving a little bit of room gives us room for a VIA without worrying about bleeding the solder out on either side. I'll move that up a little bit. I guess it doesn't really matter. Well, I know we can't do the same fan out down there because we have capacitor on the other side. One tip when using KiCad, make sure and learn all the keyboard shortcuts, because you're way faster if you're just doing mouse with one hand and then keyboard with the other. So if you want to connect a track, the shortcut is X, and that'll start a track from whatever you're hovering over. Okay. And then also selecting the track will also highlight all the components that are connected to that. Okay, so this one, oops. If you want to move something around, then click on some part of it and then hit M. It's another, super common shortcut. Yeah, with the keyboard you get a lot. I mean, it's kind of the terminal of PCB CAD, just in that it takes a little getting used to, but then you end up being way faster. Again, feel free to use the chat. Like, don't be shy. Ask me anything. If it's too off topic, I'll save it till the end. But otherwise, go for it. I mean, even if it's off topic, you can ask me anything. I'm basically just here to share some knowledge and hang with nerds. And so yeah, even if it's super beginner stuff, go for it. I'm here to spread knowledge. Okay. Just be mindful that there's a bit of a delay before I can actually see the chat and then answer, because the stream has a delay. But on my second monitor, I got the chat up, so I'll see when you ask anything. Okay, so we got two here, and then what is this? Oh, this is the ferrite bead. So this is yeah, this is kind of decoupling the different power nets from each other. Uh, uh, Ferrite beads will cause some inductive resistance, but in contrast to an inductor, they usually don't store that and give it back to you. They just turn it into heat, or at least they turn a lot more of it into heat, right? And so if you want to dampen like cyclical noise, then if your if it's not structured noise, then you can get away with an inductor. But if it's like recurring at the same frequency and whatnot, if you use an inductor, you could theoretically hit some self-resonant frequency and actually make more noise by putting an inductor in between, right? Because the inductor takes the energy when there's a transition, and then it gives it back eventually, right? It goes from voltage, current change to magnetic momentum, and then back to current, right? And so, yeah, so if you're trying to isolate different power nets, noise on the power rails often is some frequency and cyclical and whatever, and yeah, I mean, you could like theoretically try and calculate what the self-resonant frequency of your decoupling capacitors and your inductor are, and rule out being able to seesaw it up into some problem, right? But that gets actually somewhat complicated because you have the derating of the capacitors, you also have aging of the capacitors, you also have some parasitic capacitance. Yada, yada, yada. Just use ferrite beads to isolate different nets from each other, because then, you just turn the noise into heat and it's fine, right? Yeah. Now you could probably also get away with just using 0-ohm resistors rather than the ferrite beads. Like it's, less optimal, obviously, but just because this ferrite bead is there, it means that the nets are only connected at one point, right? And so they're going to crosstalk with each other a lot less, because the point they're connected at is going to be also decoupled, right? Yeah, with these two pins, I guess one pin could influence the other. Yeah, I'm not really sure why I didn't decouple both of those. Maybe I should add an extra cap and just do both of them. Oh, it's a 10 micro, but I still don't really have enough. I wonder why I only have that many. Let's look at all of those. So is there anything that's like flying around somewhere else or I lost it or something? No, these are all very close. Okay, that one's going there, and the other ones are already at their places. Looks like I don't have enough caps. I wonder why I got away with that. Well, I mean, yeah. You know, there's the joke, right? Like if, uh, for a mathematician, like 1 plus 1 is 2, whereas for an engineer, 1 plus 1 is like 3 or 4, just because we want to make sure that we don't, wait a minute, why can't I drag that? Oh, okay, because I just can't do it with the arrows. I'm not sure why I couldn't do it with the arrows, but anyway. Then the joke for a nuclear engineer, 1 plus 1 is like 100 because you want to be very sure. Wait, why can't I copy and paste this? Or do I have like some window open or something? Oh, because I'm hitting the wrong key. Sorry, everyone. Odin's stupid again. So let's add 2 of these so that we make sure that we definitely have... Oh, this is a stupid grid thing again. I hate it when the grid does this. Okay, well, if we do everything, and we do G, there we go. Oh, now the capacitors, yeah, there we go. If you select the component and hit G, G is like drag, preserving connections. I don't know why it's G, probably because all the other logical uh, letters were taken. But yeah, if you hit G, then it will drag the component while preserving connections. And so that will also make it snap to grid. And so if you're dealing with grid problems, then that's a good way to deal with it. Again, yeah, these are kind of the kinds of tips and tricks that I wanted to show here because, like, if I'm doing an instructional video, I'm probably not going to explain what grid problems are, but just happened across them. And yeah, okay, so now we have 2 extra capacitors. Let's update the board. And there they are. Because that way we can put the big one right next to the ferrite feed and put the small ones here. So you're the big one, you're the odd one out. I'll do the 1 microfarad here. So we have them all the same value. We probably don't want them connected here again because one's going to potentially, if one of them is noisy, then it's going to crosstalk more into the other one than if we connect both of them to their own respective capacitor and then connect the capacitors to each other, right? Yeah, so since we have room, put the big one here, and then the feed here. Okay, we're almost done. Famous last words, obviously. Okay, so these are I squared C. These are going to be running at like high kilohertz something. So this really doesn't matter. I just have to make sure they get out. And reset is, there's going to be low ohmage resistance and whatever. Okay, these, what are these? 37, why are they not connected? Switch. Oh, there it is up there. So 37, pin 37. Yeah, just as a sanity check. Oh, the LEDs. Well, we're in a waterproof box. Then the LEDs are too much work, so that's fine. Those can all be no connect. Yeah, if I had, if I had network, yeah, RJ45 jacks, then I would be connecting those lines to the LEDs of them. But since I don't, then I'm just going to leave them all unconnected. Okay, what else do we have power integrity wise here? I wonder why we have 2 pins there again. This is again going to be better to save them from messing with each other than if I were to just do this, right? I just do this and one of them's noisy, then the other one's going to see the noise. I mean, generally, again, gut feelings speaking, right? Uh, the chip designer is not going to be really noisy, as in switching heavy loads or whatever, on a pin which is going to be noise sensitive, right? I mean, that might be why they made 2 pins out of this, because one of them could potentially be noisy and the other one's noise sensitive, right? And so if we connect it like this, then the capacitor is going to be damping whatever's coming from the one so that the other one doesn't see it as much. So that's why we have to lay it out like this to be careful. So what is this guy? Oh, that's the big one for the 3.3 volt. Okay, so how do I want to lay this out? I mean, the big one's basically just giving us bulk capacitance for the lower frequency draws, right? Because if we're switching a large load and we actually have to send power for a while, then the 1 microfarad capacitor is going to start to lose charge at some point, right? So that's why you need the bigger bulk guy. You probably don't need it. I mean, I'm sure there's a bunch of these switch chips that have been sold without the big one, but they don't cost anything anymore. And just to be, just to not have to think about it, half a cent for a capacitor is not a problem, at least in the volumes that we work with. Okay, wait a minute. So that's, oh, so here we're going from 3.3 volt analog, or VA, whatever VA stands for, to this. So this is the ferrite. Just go like that. And there's probably some capacitor flying around here, which is, oh no, this is just the normal 3.3 volt rail. So this is connected to all the other stuff. I get it. Okay, so we're done with that. So we can put this somewhere in the middle. And we want to be able to fan out. Oh man, this is all kind of screwed up though. So we definitely have to change what's connected to what. So I guess I'm going to put it like here-ish. And then we need to start changing where stuff is connected to. Oops. Let's put it back up here so that we have it still selected. Because I can't really select it when it's down here because I can get all the other stuff. So I rotate it. Does it eventually look better in some way? Not really. No, it's just kind of not logical how that's all connected. Yeah, so I think this is probably roughly the rotation that I want. And then, yeah, so half. So this guy is going to be connected to the compute module. So I have 3 on this side and 4 on that side, but I'd also need room for the power Ethernet chips on the left-hand side somewhere, right? So why don't I just put it here? Make sure we don't run into problems. Now, oops, made a wire. Okay, so this guy here should actually be connected to this port. So pin 58 should be connected to whatever ETH magnetics 4. Okay, how are we going to best do this? Because here, but then how do I see which? Okay, I'm just going to select this one and see which one it is. Okay, that's that one. So 4 is the one I was saying, right? Okay, so this one should be connected to wherever 1 is connected right now. So why don't we just kind of do a quick sortie-ish kind of a thing. Move these around. This is where subsheets really come in handy. So I'm just going to swap out everything that's wrong, and after I swap enough, then it'll just work. Oh no, grid problems again. It's because the wires are the wrong grid? Oh, okay, I guess I just grabbed it wrong. That's probably the thing that bugs me the most about KiCad is the grid problems. Okay, let's update this and see if we screwed up. Hey, okay, so that is connected to that guy. And so I guess this one we want connected, because this guy's different. So do we have anything on this side? No. Okay, so this one, we want this one to be connected to the bottom one here. And so that is, what? Why are they named different for some reason? Oh! Yeah, we have the one that goes to the land grid array. Where do we want to put the stuff that goes to the land grid array? Actually, arguably, we want to connect that to the land grid array and then connect that to that one. Okay, so this needs to go where... So this is what? That's magnetics 8.7. Oh, no, that's the Phi to Phi one. Oh, okay, so that's going to be a lot more work if we want to swap that out. Screw it, it can just stay there. I think I might actually move these resistors onto the land grid array board, because depending on what the board is, you don't actually need them. And so if it's, you know, a property of what the board is, these probably shouldn't be on here anyway. Yeah, I think I'm going to just change the piggyback boards, because they're going to be a different format anyway, so they're not going to be compatible anyway. So why don't I just get rid of this one? And on the Pi Compute module land grid board, like that option, then they'll just go on there. Okay, since I don't think I even have a footprint for that, that means these are just going to go no connect. Yeah. Okay, so now this connecting to that is already logical, so that works out. So now this connecting to that, again, is logical, so that works. What do we got next one? So this one, where does this one go? Let's select X and see where it goes. Okay, this going to that, that's still actually logical, but maybe I rotated it wrong, because, oh shit. You can also hit Control and then, oops, hit Control and then deselect some of the selected stuff. And so we might be able to get away with still rotating it. Here we go. Yeah, I think this is actually better, because otherwise we would have gotten just way too many tracks up there. So let's put it something like here. Okay. So we have these going there, and these going there. these going to that one, and these going to that one. Okay, that's still logical. Now it's illogical because this one, magnetics 3, should actually be going to magnetics 2. So 2 and 3 need to switch. Again, yay, I used cheats. So let's just switch these two around. Oh, wait, I'm going to need to switch the connectors as well. Oh, well, cross that bridge when we come to it. There we go. Yeah, because that just switches the magnetics, so now the magnetics are going to the wrong connector. So I switched around 2 and 3 just now, but before that I also switched around others. So why don't we go... These two I switched. Oh, damn grid. Oops. And then I did the top one and something down here, right? Let's look how bad it is now. Okay, so that one's connected to that. So what is this one connected to? Way over there. So that's East Magnetics 1 and East Magnetics 4 need to switch, but they're connectors. So that's 4. And where's 1? 1 and 4? Really? I remember it being a lot further down, but we'll see if this actually solves it. Ah, grid strikes again. Wow. Again, I hate the grid. I hate the grid. This is also confusing because in the layout program, the keyboard shortcut for a track is X, whereas in the schematic editor, it's W for wire. But after a while, you get used to it. Okay. So let's see. Okay, so that one looks good. That looks good. That looks good. This one I already routed and looks okay. That one looks good. That one looks good. Okay. So now I think we probably have to decide where the power over Ethernet controllers go. For these 4, I think we're going to put it on this side of the chip. And then for these 4, I think we're going to put it down here. So I think we still are not really in an optimal spot here. Let me move this to the left so we have room for the power of Ethernet controller. Okay, deselect that, hit Control and click, we'll deselect it, and move this over here. Probably actually a lot, right? Because that'll also shorten a lot of these connections, which is also good. Okay, I should be able to route that pretty well. Okay, so these guys are going all the way over there, so that actually might be a little tight. I guess that would be an argument to move it back actually a little bit. So let's deselect these and go back to where that becomes routable around the whole crystal and whatnot. Okay, so something like that. So then We have power of Ethernet controller, which is connected to here. Which of them is that? Okay, so that's that one. So let's make sure that we have those sorted properly after we switch stuff around. Okay, so this guy's power over Ethernet is going to that controller. And this guy's power over Ethernet, where are you? There we go, is going to, what? That's going to here, fuse, and then that's going to that controller. So we definitely have to swap stuff around there. So this is, oh, wait a minute. Let's figure out where the other ones are going before I start swapping stuff. Okay, that's also going to the left controller, I think. Yes. And where is this one going? Yeah, okay, there. Where's the other end of the fuse? Oh, so we're 50-50. Why don't I sort the fuses over so I don't screw this up? So this fuse is over here. And this fuse is also going over here. Okay, so this magnetics is going to need to switch to the other power over Ethernet controller so that we have those logically set up. I'm not sure how that worked with the routing last time, but oh, that's why. Yeah, okay. Oh well. I guess I could have also just swapped the lines here. That might have been a better way to do it. But I'm already so far down this path that I'm going to do it this way. Okay, so that was this POA thing going to the wrong controller. And then what are we going to swap it with? That is still correct. Where's that one going? Okay, so this is TR8. Where do we see that? Yeah, East Magnetics 8 and East Magnetics 2. We need to switch. So where's 8? There's 8. Canal 8 needs to switch with 2. Nope. Dang grid. So, okay. 8 needs to go to 2. Where's 2? It's all the way up here. This is going to look really ugly. Okay, now that one needs to go all the way to 8. Hopefully not. Oh, yeah. Well, we'll fix it in a minute as far as the spacing. After we make sure we got it all fiddled around correctly. Okay. So, I guess I could just do the... Okay, that one's going there. So this transistor is now going there. This transistor is now going up there. And this transistor is going there. Okay, so everything's good, I think. I hope. Famous last words, everything's good. So let's see. So we have our power Ethernet controller, and I already apparently laid this out somewhat good. The controller has basically 4 different channels. So, oh, we're already coming up pretty close to the end. Wow, time is flowing. Um, so yeah, so we have, basically what the controller does, the reason the controller is there, kind of going back to the last episode, why don't I draw this for you guys? Why the controller exists in the first place. Oops, I have a text marker. I can't delete the text marker. So my super high quality welcome message. Okay, I theoretically have a pen which I can actually draw on the screen with here somewhere. Oh, there it is. It's magnetically sticking to things. There we go. So, if I have, oops, that's the wrong tool. No, I took that away. Okay. Odin being incapable of things. Okay, so we have our Ethernet magnetics, right? Something like this, and then we have the wire, and then again on the other hand side we have our magnetics, and let's draw the magnetics in green. So we have a ring core here and a ring core here, and so if power flows like this here, because we're changing an edge, right? Well, then it's going to flow like this here. Is it going to flow that way? Well, I guess depending on how the wires are wound, but who cares? Just for illustration purposes. So the change in voltage is going to induce a current that's going to flow around here in a circle, which is going to change the voltage on the other end, and so that's how signals propagate through the network, right? But if we're interested in how power goes through the cables, then if we take the center of this and the center of this, then those are going to be unaffected by the whatever bits are going across the wire, because they're the middle, right? So if the top goes up and the bottom goes down, the middle stays the same. The top goes down and the bottom goes up, middle still stays the same, right? So that's the whole trick for power over Ethernet is, you have at least two differential pairs. And so if you run current through the center taps, then you can power the device without messing with the Ethernet signals, right? Problem is, power over Ethernet is newer than the Ethernet standard. So there could be older devices that are terminated with some resistor to ground, right? And so if we put high voltage, 48 volts going through here, we're just going to fry the resistors of the old legacy devices that predate power over Ethernet. So what we need to do as a power over Ethernet controller is, wow, that's a really tiny eraser. How do I make it bigger? That? No, wait, here. There we go. Now we got a big eraser. Say hello to my big eraser. Anyway, there we go. Okay, so we need to have a switch that'll turn on power if we detect that the other side is some specific class of device. And so we have a chip on the one side, which is called the power source equipment, PSE, and we have a chip on the other side, which is a power device, PD. And the two of them play around with voltages and resistances and figure out that the other one's the right device and then turn it on. So that's what this controller chip does. And so the controller chip is able to do that for 4 different ports, right? So it basically has the same circuit 4 times over. And so if we switch back to schematic, here we have, a MOSFET and 4 resistors, and another MOSFET, another 4 resistors, and another MOSFET, another 4 resistors, and another MOSFET, another 4 resistors. So those are the 4 channels. And then for each of the ports, we also have a fuse and a transient voltage suppression diode. and I think a capacitor. Yeah, there we go, capacitor. So why don't we put the fuse, the TVS diode, and the capacitor close to the magnetics. Oh, okay, so that's why this guy is already here, but since we rearranged him to a different one, he needs to go somewhere else, and whoever's here needs to go here. 48 volts, and this is the right line. No, this is the wrong line, wrong one. That guy needs to go up here, and then who needs to go here? That guy. So again, this is the same same thing we had back in the beginning, or last week with the transient voltage suppression. Since the wires go outside of the box, then there could be somebody who's pulling them up or down or whatever. That somebody could be lightning or who knows. And so we definitely need to change any voltage that is not the voltage we're expecting into heat, and that's what a transient voltage suppression diode does. And we want to connect everything else that comes after that TVS diode through the diode, because we don't want voltage drop killing us anyway, because transient voltage suppression diode will clamp it, but only locally. So if we make sure that everything else goes through locally, right? So, like this and not directly like that, right? Then we should be fine. Okay, we can just put the fuse here-ish. And then we do that for all the ports. And so fuse and whatnot is going to go next to the port. The capacitor is going to go next to the port. So we get all that away from here, and then we're just left with this. And do I have room to put this somewhere where it doesn't screw everything up? I think actually I want to put it there, because that will give me a little more room. And then we can just route everything. I don't have, yeah, here's where the LEDs were, so I'm not going to have a whole lot of wires going through here. I think this is a good place. So I guess we're just going to spend the rest of the time, as long as nobody has questions in the chat or anything, we're going to spend the rest of the time just routing this out. Okay, so this is the 3.3 volt regulator. That's going to come down here somewhere, I think. Probably not going to leave it up there where it was. So I guess this one needs to go close to that. So I don't know, do I move this closer just so that that can fit between the... I guess we're not really screwing anything up by moving it down. I can put this up here, so it's close to everything. One, yeah, I mean, we actually probably don't need a millimeter wide track here, because at 48 volts and what, nominally 15-ish watts or something through PoE, that's not a whole lot of current. I mean, narrower tracks probably do, but I don't care. Leave them like that. Let's see. So we have probably a capacitor and a fuse that match this guy. And they're down here. So let's move them up. What is this capacitor connected to? Oh, yeah, that was because of the switcheroo. So can I get around this? Yes, I can get around this. And then fuse, and then we got all the ones for that one, except this fuse is going there. So we need the fuse that is associated with this one. Okay, there it is. Oops, the wrong key. Hit E rather than R. R rotates and E is like extra information. Okay, that's going this way because we want to be able to get out that way to route those. Okay, where is the TVS diode associated with that guy? Okay, it's down here. And he's got his little capacitor with him. So let's go here. Okay, rotate it like that. And scooch this guy to... Can this guy scooch down? Yeah, he can. Okay, yeah, so I do have to worry about height with these things, but the tall part is actually about the size of the inner courtyard here, and the nuts that screw these connectors in to the case are about as big as the blue part, so that's about as close as I can cut it because the nuts might not be in this angle, right? So if you can imagine, this nut turned around, there'd be the point like here-ish, and so yeah, so this will still work as far as height. Okay, so then I got the transient voltage thing there. I guess, yeah, I want to do the capacitor next. Oops, is this thing crashing on me? No! I think I need to upgrade my KiCad. This happened to me a couple of weeks ago too. It sometimes just randomly crashes. Well, that kind of ends the stream because I'm going to have to restart this, I think. And other than my olds. Yeah, I think I'm going to upgrade before next time because this, well, at least it didn't like crash in the middle. Hey, everyone can see I use German Windows. Let's see when the last autosave was. I hope it's not forever ago. Yes, let's see, finger crossed. Oh, it was a while ago. Oh no. Oh no. Okay, well, I think before next week's stream, I'm going to get us back to where we were-ish. Because this was, I mean, was it after or before we swapped them all? It looks like it was after we swapped them all, at least. Yeah, and then I'm also going to upgrade. Oh, that one being right meant we actually swapped that out. So yeah, so it wasn't actually all that bad. No, it was that bad because that was the one we swapped out. That one's probably still wrong. Yeah, no, that was a while ago. We lost quite a bit. So I'm going to bring it back to that same spot before next week and just leave it here. I'm quite happy to answer any and all questions that come in the chat. That's we haven't been quite as lively with questions so far. So think of good questions, and I guess I'll see you guys next week, and we should be able to finish the board next week. We don't actually have a whole lot left to do. I mean, if we zoom out, the fan out here should work pretty well because we thought about it ahead of time. I mean, these two are going to have to move to the right, and then this one will go up here like we had it before it crashed, and then this one's going to go over here. We may have to change its layout a bit to get it to squish in there, but then we should be pretty done-ish. I mean, we'll need to do move all the sync screen around, but I don't know if you guys really want to watch me do that because it's pretty clear like how. You just, put it in spots where it's visible. Um, I might in 2 weeks show you guys like how I order it. Although I wanted to do a start to finish in 2 weeks. Started in 2 weeks, and it'll probably be like three-ish, maybe 4 episodes, depending on which board I end up doing. There's a poll for which board, so vote for which design you guys want. Um, yeah, if we end up doing the big one, then it'll be like 4 episodes probably. If we do the small one, then it'll maybe be three. But at the end of that would probably be the time where I show how to do the ordering and component association and whatnot. Because then we'll have like one start to finish, the whole board. Um, and Yeah, so looks like we're getting up to time, and I don't really have a whole lot to show because I have to fix all this first before I can show you guys new stuff. So yeah, I guess thank you, and see you all next week. I will continue to do this as long as it's fun, and it's been fun so far, so probably I'm going to do it for a while. So yeah, if you think you know someone who might have fun watching, then tell them, and retweets are obviously always appreciated. uh, Take care, guys, and see you in a week.